To avoid manually programming robot motions, imitation learning is typically a good alternative that enables robot motions to be acquired from expert demonstrations. To learn versatile behaviors, most learning from demonstration frameworks require a large number of demonstrations, which can be a tedious task, particularly for non-expert demonstrators. Effective models for imitation learning can be learned using large scale models. These are, however, typically black box models, while many applications such as robot assisted therapy have interpretability requirements. Interpretability is particularly important so that behaviors can be modified more easily. In this work, we propose STORM, an interpretable graph-based learning from demonstration framework using skeleton data. STORM combines graph pre-training and subsequent demonstration-based adaptation for acquiring motions corresponding to different motion classes. This diagram illustrates the system architecture of STORM. The general idea behind the framework is to learn joint-specific constraint graphs, which essentially encode known inverse kinematic solutions. New demonstrations are then used to expand these graphs, while Gaussian mixture models are used to represent trajectories corresponding to concrete motion categories. To solve the correspondence problem, we learn a neural network that maps human joint observations to robot joint angles. This is learned from a labeled dataset of motions. Before learning from demonstration takes place, we initialize the graphs by letting the robot create an initial model of its embodiment. We concretely use random motor babbling for this purpose. As already mentioned, when new human demonstrations are received, the library of graphs is expanded as necessary. The expansion process ensures that new observation points are connected to the rest of the graph, while preventing redundant points that are too close to each other. The information contained in the graphs can be used for planning paths in configuration space, but we obviously also want the robot to execute motions corresponding to the demonstrated actions. We learned models of demonstrated action categories in the form of Gaussian mixture models, and then use Gaussian mixture regression for trajectory sampling. When learning motions from demonstrations, information about obstacles is not included in the graph. To enable online obstacle avoidance, we remove graph points that intersect observed obstacles, and then plan a new path that is as close as possible to the originally desired trajectory. To evaluate the individual elements of STORM, namely the cost of motor babbling and the path planning and obstacle avoidance performance, we perform various experiments with three different robots: Lux AI Qt robot, Aldebaran Now, and a custom platform that we refer to as Freddy, which has a mobile base with two Kinova Gen 3 arms. Details about the evaluation can be found in the paper. Qt Robot and Now were also used in a user study in which the user acceptance of the motions produced by Storm was evaluated through a series of pre-recorded videos. This includes a comparison of Storm with our earlier approach that was specialized for Qt Robot, an evaluation of the motions on Now, and an evaluation of Storm's ability to perform online motion imitation. Overall, the user evaluation indicates high acceptance of the motions produced by Storm. The results of this paper are promising, but there are various aspects that we would like to address in future work. First of all, in this work, we only evaluate Storm on upper body motions. This is not a conceptual limitation of our approach, but an explicit evaluation of full body motions needs to be performed as well. With respect to the learned graphs, it could happen that some nodes are added during babbling or from demonstrations, but which are rarely used. To optimize the graphs and reduce the memory requirements, it could be useful to prune rarely visited nodes from the graphs occasionally. In this work, learning is performed purely based on skeleton information, but it will be interesting to consider an extension that enables language commands to condition motions. Finally, in a storm, dedicated expert models in terms of Gaussian mixture models are used for representing concrete motion types. In future work, a global generative model of motions could be learned as well. This could perhaps be used to generate synthetic trajectories for additional learning.